Hi, I'm Stephen Grubb, a global optical architect at Meta. My colleague Joseph and I are going to talk to you about the global fiber mesh network that Meta has built and how we control it. First of all, I'm going to start by telling you about our subsea global fiber mesh network, how we've scaled this global mesh network and the challenges we've encountered. Then I'll talk about the innovations that we've had to drive in this typically conservative industry in order to keep up with our scaling needs. And then finally, our connection to terrestrial networks and data centers. Then I will pass it off to Joseph to tell you about how we control this global optical mesh network. First of all, Meta has an extensive global subsea network. This is necessary because we have 3.6 billion worldwide monthly active users on one of our core application platforms. So a very large number of users, and more than 85% of these are outside of the US. So an efficient, reliable global network is absolutely core to Meta's business. To this end, we've had taken on partners and we've built more than 150,000 route kilometers of subsea networks. And we've had to scale that over the past several years. For instance, when I started at Meta, we had only one subsea system build in 2015, but today we have more than 20. So that's a massive scaling of these very large global builds, which present some exceptional challenges and opportunities. First of all, I'll tell you a little bit about our traffic. I've normalized our traffic since I've assigned the value that we had in 2016, a value of 1. And I'll talk about our relative increase in global subsea traffic. So to date, since 2016, we've increased by 13 times, which is no small number. So that's a pretty large number to scale in a few years. But if we look at the next several years, we can see that we have to scale an additional 460%, going up to a factor of 60 from the value that we started at in 2016. So that's a very large number to scale. This is a classic exponential scaling, and this is necessary in the next several years as we bring on several new international data centers, such as the one in Singapore, SGA, which I'll tell you about in a little bit. So this kind of exponential curve is challenging, even if you can deploy on a nearly instantaneous time basis. But deploying subsea networks is even more challenging for several reasons in order to keep on this exponential curve. First of all, it has to do with the massive scale of these projects. These are truly tremendously large international engineering projects. Only 3 companies in the world are capable of deploying these systems. And you need ocean liner type ships in order to survey the routes and load the cable and deploy the cable. The top photo shows the person guiding the cable into the hull of the ship, preparing for a trans-Pacific deployment. So these projects are absolutely massive and require a tremendous amount of coordination between an international team. Secondly, there's a 4 to 6 year time frame for each project due to the massive complex permitting, the geopolitical issues, and the tremendous coordination that has to occur between all of the parties and the landing parties as well. So you can think of that exponential demand curve. So you can see that if in the next 4 years, where we're really starting to kick in that additional 460%, we've had to initiate those systems several years ago before we see that massive increase in traffic. So it's quite a bit of time delay in order to intersect an exponential growth curve. Also, traditionally, this has been a conservative and slow-moving industry, dominated by traditional telcos, which carry traditionally voice traffic and small amounts of data. So we've had to partner with like-minded partners such as Google and Amazon, which move at the same pace that we do and have the same kind of exponential scaling needs that we do. And lastly, the technology was becoming a limiting capacity in these systems. For instance, if we had remained static in the technology, where I showed you that we started building in 2016, we literally would not be able to build systems fast enough in order to meet our demands. So we've actually had to push the industry towards new technical directions so that we could meet these capacity needs of our own. I'm going to tell you about the 2Africa submarine cable system. This is the world's largest system. This shows at 47,000 kilometers. This shows a landing in Gabon, and we pan out, do a Google Earth flyout, and you can see the massive scale of this system. It actually has 42 landing stations in 33 countries. And as I said, it's 47,000 kilometers, and it spans 3 continents: Europe, Africa, and Asia. So actually, it serves the largest number of potential users in the world at 3 billion. There's approximately 1.2 billion in Africa, then an additional 1.8 billion in the Middle East, India, and Pakistan. So a tremendous scale system. This shows a 2D representation showing the 33 landings that we're doing. And it should be noted, too, that these subsea systems have been shown by various studies to have a very positive impact on the economies of developing countries. For instance, Africa got some smaller scale subsea connectivity in the late 2000s. And there was a study that showed that the gross domestic product of the Republic of Congo increased by 19%. And so there are many correlations there. So this new, much larger capacity system is going to breathe new life into many regions. So as I mentioned, it has the potential to connect 3 billion people. I'm also going to talk about our 2 new systems, Echo and Bifrost, which are the first direct US to Singapore cables ever built. And these actually connect the US, Indonesia, and Singapore. This primarily for us is to connect to our new data center coming online in Singapore, SGA. When complete, these 2 systems will actually increase the total Trans-Pacific capacity by 70%, which is an extremely impactful number. And this is due to the technological innovations of SDM, which I'll describe in the next slide. It's also the world's largest optical segment at greater than 16,500 kilometers. So very, very notable systems here. We've had many firsts in the subsea industry. I told you about the largest scale project to date, 2Africa at 47,000 kilometers, connecting 33 countries, serving up to 3 billion people. We also have the largest capacity subsea system ever announced, and that's a new transatlantic system at 500 terabits per system. And this actually, in terms of capacity, is about 200 times the capacity of the transatlantic systems deployed in the early 2000s. So again, it's our innovations coming to light here that are driving the capacities of these systems. And the first one, which I note below, is that of SDM, or spatial division multiplexing, which increases the subsea system capacity by a very large amount. We've driven this innovation in the industry, and this is absolutely necessary in order to keep on our exponential scaling curve. Secondly, we've replaced the copper conductor used in these cables with aluminum. Aluminum is lighter, cheaper, and more energy efficient than copper. So that's going to have a big impact in future cables. Thirdly, we're investigating a new technology, that of mid-ocean power buoys. And that's an alternative green energy source that harnesses the green energy sources of wave power and solar power. Those 2 actually have seasonally complementary energy profiles such that they smooth out the total energy supplied at 25 kilowatts throughout the year. So we're starting to do some sea trials of this exciting technology. Lastly, we've developed a very efficient modeling tool called Atlantis, which actually tells us where to route the cables so that we have the most reliable network, the most reliable subsea network. It turns out that there are a lot of geoactive formations which can damage the cables, and then we avoid the high shipping lane, anchor drop areas, which damage cables. So our actual cables are actually quite a bit more reliable than previous subsea cables. So we've driven all these innovations. These are necessary to keep moving the industry forward and meet our capacity needs. Lastly, I'm going to show you how we tie in our subsea networks to our terrestrial networks. I may have time to show you our North American network here. And we have some trans-Pacific subsea systems coming in from the left to this network, and the Atlantic subsea systems from Europe coming into the right. And we connect into our North American network. For instance, we've laid more than 3,600 route kilometers of optical fiber in North America. And each of those cables has several hundred fibers. For instance, our newest cables have 432. So Meta's announced 21 global data centers, more than 200 colo facilities, and more than 5,000 caching facilities. So we rely on this global optical mesh network to connect all of these. So I've given you a flavor of how the network that we've built, this global optical mesh network. Now I'm going to hand it to my colleague Joseph to tell you how we control this network.
Thanks, Steve. As Steve mentioned, Meta has built a global optical mesh network. It's a lot of fiber. And right now, I'll talk about how we control and operate it. So for starters, why do we need so much fiber around the world? Well, Meta is pivoting around AI in the metaverse. AI means a lot of compute happening. It's GPU powered right now in our data centers, which requires a lot more capacity ingressing and egressing our data center sites. And the metaverse means new applications that are closer to the user than ever before. So a lot more sites requiring low latency communication globally. Now, why do we need so much fiber? I mean, Steve mentioned, 500 terabit systems at some point in the near future. Well, looking at our actual traffic growth, traffic has been growing exponentially within Meta's backbone, and we forecast that this will continue. There are a couple of key segments within the capacity that we build. The first, origin to origin, refers to traffic between data centers. And so this would cover things like our AI training and inference, which is distributed across sites around the world. The second category is what we call edge to origin, and this is traffic to our users or from our users. The volume is a lot less, but this is pretty critical because if it goes down, our users notice. Now, the exponential growth that I mentioned is really felt and powered by the optical network. The number of channels within our network has been going up by about 50% year on year for the last few years, and we forecast that this will continue. And ultimately, this supports about a 90% increase year on year in the IP capacity, which is almost doubling. We've been able to take advantage, though, of the fact that there have been improvements in the amount of capacity that each channel can carry. Hence, the rate of growth in terms of optical channels isn't as steep as it is for IP capacity. Now, moving on to how we actually implement the scaling. Scaling IP is a little different from scaling in the optical world. The techniques for scaling IP networks are fairly well known. There are a couple of things that you can do. Vertical scaling generally involves increases in the amount of capacity switched per switching element in your network, as well as increase in the capacity per port in your network. So you can imagine going from 10 by 40 gig to 20 by 100 gig as an example. Horizontal scaling generally involves having wider fabrics. We've taken advantage of this within data centers, and closed networks, as an example, are a pretty well-known way of scaling networks horizontally. In contrast, in the IP network, we have a couple of levers that we use in scaling. The first of them is scaling capacity, and this is a close equivalent to scaling vertically, as I mentioned, in the IP world. We can scale capacity by having more fiber at each site, which allows us to have more channels and therefore more IP circuits carried per site. You can also do that by having more channels per fiber, and you can do this by, as an example, going from the C band to the L band, which effectively doubles the amount of bandwidth per fiber. We're also able to scale horizontally. The closest way of describing this is by thinking about a topology and thinking of horizontal scaling as just having more potential connections per site, so more degrees of freedom in terms of where you can connect. And in the optical domain, we do this as an example by taking advantage of things like wavelength selective switching. That's just routing having the ability to route channels to more sites from each source or destination site. Now, we've been able to achieve this scale thanks to our design philosophy. Meta's network has grown tremendously over the last few years, but our operational team has not. And we're able to do this thanks to the fact that we're very consistent about the way we build, and deploy technology. First, we have a dual vendor network. This is harder than it sounds because, unlike the IP domain, most optical hardware isn't interoperable across vendors. So if you have a transponder from vendor 1 at one site, all channels being sent from it need to terminate on transponders from the same vendor at the far end. We also focus on having not more than 2 generations of hardware per segment in the network. And again, this is a little tricky because even for a single vendor, generally optical hardware isn't interoperable across generations. Finally, we focus on simplicity in build, deployment, and operations. As an example, we have pre-built racks that are shipped to a site and installed, and that makes bringing capacity in and out of service fairly quick. All right, so I've spoken quite a bit about topology, but what is that? In practice, imagine that we're sending bits from the egress interface of a router in the Bay Area to a peering router somewhere in Lagos. In reality, this involves our bits traversing across hundreds of unique elements across dozens of sites around the world. And each of those elements needs to be captured and stored somewhere so that we know what configuration to send to those elements to support the capacity turn-up. We achieve this using our topology model, which covers all the unique elements in the network as well as the relationships between them. For example, IP circuits, which are relationships between IP routers, all the way through to optical channels, which are really relationships between transponders at both ends that are connected by an optical signal going from one to another. We also model the actual physical optical hardware, such as rails, which are aggregations of optical fibers connected by inline amplifiers from end to end. This particular model also allows us to have various views of our topology, both the current topology as we desire it, as well as the discovered topology, which I'll describe in a second. So what is topology discovery and why do we need it? Networks are real living things. They're not static and they change in time. As you can imagine, at any point in time, we have hardware being introduced into the network and hardware being taken out of it. And yet we need to always have a real-time view as to what the current state of the network is. We achieve this via our topology discovery framework. This is a set of probes that are continuously pinging the various boxes in our network and retrieving their current operational state, as well as some telemetry, all of which is stitched together to build a real-time view about the network. This relies on having multiple protocols, and that allows it to be vendor agnostic. So we support both pull and push-based polling across protocols from netconf all the way up to CLI. Now, once we've discovered our network and we know what we have and where it is, the next step is to actually turn up capacity on it. We've built what we call an optical pipeline that takes in a set of demands, such as 10 terabits from data center A to data center B, and turns that into a set of channel plans, which are specific sets of configuration that are sent to the optical elements in the network to turn up capacity to support the IP connectivity required. Our optical stack is in-house and has been operational for a few years now and has allowed us to scale in the manner that we have. We've also been able to automate the actual deployment, which is the sending of configuration to the network elements. And so capacity turn-up right now is close to being fully automated without necessarily having users in the pipeline. So moving on to the next stage in operations, fault detection. As any optical engineer will tell you, one thing we deal with in the optical world are faults. They happen all the time. Fibers traverse the real world. They go under roads, above bridges, and on overhead fiber cables, and as Stephen mentioned, even on the seabed. And as a result, we have things like fiber cuts happening all the time. And so successfully operating an optical network requires a lot of investment in fault detection and remediation. There are a couple of ways to doing this, which we generally classify as bottoms up and top down. In the bottoms up case, we infer what is failed based on a known failure signal coming from failed elements. And in the top down case, we infer what is failed from the capacity that is affected by a failure. I guess an analogy for this is imagine if you're operating a local utility company, a water utility company, and you're trying to build a system to detect mains leaks. In the bottoms up case, you might deploy probes inside of mains pipes, which would alert you if a pipe ever had a leak. And in the top down case, you might deploy probes in users' houses that would alert you if any particular users had lower water pressure coming to their homes, from which you could potentially infer which mains might have triggered this water pressure drop. In the interest of time, I'll just focus on how we do bottoms up detection here. We have an entire stack built that takes signals from all the elements that capacity could have traversed. Now imagine a case like having a fiber cut, and that would disconnect the connectivity between two inline amplifiers or ILAs. In that case, the two ILAs would send signals over various protocols depending on the manufacturer and model. And our discovery framework would pick up those signals and based on our current view of the topology would allow us to stitch together a representation of what capacity, which actual IP capacity, as shown by the routers on both ends, is affected by the failure. Now, depending on whether we actually had production capacity up, we trigger a set of events, which we call troubleshooting workflows, which include things like opening up tickets, potentially sending people onto site to fix the event, to bring down the IP capacity, as well as alerting on calls about the fact that capacity is down. This entire process is fully automated at this point. Finally, I'll just give you an example of one of the kinds of challenges that we're focused on to allow us to continue scaling our network long term. Scheduling operations across our network is getting more and more complex due to the fact that we have activities happening simultaneously at various sites in the network that may have an impact on capacity. As an example, we could have a migration of capacity or fibers at one site that could potentially affect channels terminating on another site where a project may be happening in parallel. To get this to work seamlessly without having failures, we need to have a view of the topology that gives us both a real-time version of what the network is right now, as well as allows us to predict what the topology would be like if we were to execute these operations, as well as maybe even shuffle them, change the ordering back and forth. This is fairly challenging because it requires a new view of the topology, much more complex than what I described earlier, which was simply a real-time view. All right, so I'll just hand off to Steve, now that I've talked about how we operate the network, to give you a summary about key takeaways from this talk.
Thanks, Joseph. I'm going to present some key takeaways from our talk today on wiring the planet. First of all, I told you about our global subsea network, how we've had 60x scaling in 10 years, and the challenges that brings, and how we've solved that. We've actually had to innovate and drive the industry much faster than it normally moves in order to keep up with this aggressive scaling. I told you about many firsts in subsea. For instance, our To Africa system, the largest subsea system under construction now, which can potentially connect up to 3 billion people. I've told you about Bifrost and Echo, the first US to Singapore cables that will connect our data center in Singapore. Joseph also told you about an in-house software stack for design, deployment, and control of this global mesh network, which is critical. And finally, the continued growth, exponential growth of our global mesh network is opening up new classes of operational challenges, which we will have to solve in order to continue to control our efficient global fiber mesh network. Thank you for your attention today, and we encourage you to reach out to us if you have any additional questions on our talk. Thank you.